We have now examined waves and tides, both of which involve motion, but neither of which moves water persistently across the ocean basin. Waves move energy, tides move water back and forth. What we begin today is fundamentally different. Today we begin talking about water that actually relocates. Surface currents are sustained, directional movement of water across a large distance. Surface currents represent one of the primary ways the ocean redistributes heat, salt, nutrients, dissolved gases, and even pollutants across the planet. They link the atmosphere to the ocean interior and connect tropical regions to polar regions. Surface currents begin with wind, but we must be precise about how wind actually moves water. Wind does not simply push the ocean like a hand pushing a box. Instead, wind transfers momentum to the ocean surface through friction. Air moving across the ocean surface creates shear at the boundary between air and water. Because air is moving and water initially is not, collisions occur between air molecules and water molecules at the surface. This produces what we refer to as wind stress, a force per unit area acting on the surface. When wind blows briefly, it may generate waves but not sustained current. But when the wind blows persistently over large areas, as global wind belts do, the continuous transfer of momentum causes surface water to begin moving in a consistent direction. The key distinction here is duration. Waves form when wind energy is transferred but oscillates. Surface currents form when wind stress is persistent and momentum accumulates in the surface layer. Surface currents therefore represent net horizontal transport driven by sustained wind forcing. If Earth did not rotate, surface water would move in the same direction as the wind. But Earth rotates, and that rotation changes how motion behaves. Any freely moving object over Earth's surface experiences an apparent deflection due to Earth's rotation. This is, of course, from the Coriolis effect, which we have already talked about. As a reminder, in the northern hemisphere, motion is deflected to the right of its direction of travel, and in the southern hemisphere, it is deflected to the left. This means that when wind begins moving surface water, that water does not travel directly downwind. Instead, the path bends toward the right or to the left. So the Coriolis effect does not create the motion, but it does alter the direction of the motion that already exists. Wind provides the force, Earth's rotation modifies the direction. It is essential to remember that wind applies force forward, Earth's rotation deflects motion sideways. The resulting motion is a compromise between the two. Understanding this distinction is critical. Surface currents are shaped by both wind stress and planetary rotation. Neither alone explains the pattern that we observe on the planet. When wind applies stress to the surface, only the uppermost layer of water begins moving immediately. But water has viscosity and internal friction due to the high cohesive properties of water, and that viscosity allows the motion to be transmitted downward. Let's explain this by starting at the surface. The wind begins pushing the top layer of water. Because of Coriolis deflection, that surface layer does not move exactly downwind. In the northern hemisphere, it moves at some angle to the right of the wind direction. Observations showed that this angle is often around 45 degrees at the immediate surface, though the exact value tends to vary. Now consider the layer just beneath it. That layer is not directly in contact with the wind. It does not experience wind stress. Instead, it is dragged by friction from the layer above it. Because friction transfers energy imperfectly, the second layer moves more slowly than the surface layer. But here's the key. The second layer is also subject to Coriolis effect. Since it is moving, it is deflected to the right in the northern hemisphere. However, because it is moving more slowly, the magnitude of that Coriolis deflection relative to its forward motion changes the direction slightly more than the layer above it. And then, of course, this process repeats downward. Each deeper layer moves more slowly because the friction dissipates energy and is deflected slightly more relative to the layer above it. This pattern is known as the Ekman spiral, named after von Wolfram Ekman, who first described it mathematically in the 20th century. Now here's the critical conceptual result of this. If you average the motion of all of these layers together, integrating velocity from the surface down to the depth where motion effectively disappears, the net transport of water is approximately 90 degrees to the wind direction. This means, northern hemisphere, the net transport is to the right of the wind at about 90 degrees, and in the southern hemisphere, the net transport of water is about 90 degrees to the left of the wind direction. This net movement is called Ekman transport. Students often struggle here because this seems paradoxical. Wind blows east, why does water move south? The answer is cumulative deflection through the depth. The top layer is not 90 degrees from the wind, but the integrated effect of all the layers below is. This is one of the most unintuitive but foundational ideas of physical oceanography. Now let's apply what we understand about Ekman transport to coastlines. Imagine you are standing on the west coast of North America in the northern hemisphere. Suppose wind is blowing from the north to the south along the coastline, as you see in this illustration here. That means the wind is moving parallel to the coast. From the previous slide, though, we know that in the northern hemisphere, Ekman transport is directed 90 degrees to the right of that wind. So if the wind is blowing southward, the right-hand side is westward, which means offshore. So even though the wind is blowing along the coast, the net transport of surface water is going to be moving away from the coastline. Now here's the key physical consequence. If surface water moves offshore, it must be replaced somewhere by something. Water cannot simply disappear from the surface layer. The ocean must maintain continuity. So when surface water is transported away, deeper water rises up to replace it. This vertical motion is what we call upwelling. Upwelling is the upward movement of deeper water toward the ocean surface in response to surface divergence. Now let's put this together. You already know that deeper ocean water tends to be colder. You know from the sedimentation lecture that nutrients accumulate at depth because nutrient-rich organic matter ultimately sinks to the ocean floor. So when upwelling occurs, cold, nutrient-rich water rises into the sunlit surface area. That surface layer is where photosynthesis occurs. Phytoplankton requires sunlight and nutrients. In many regions, nutrients are the limiting factor. Upwelling will deliver those nutrients. So this is why coastal upwelling regions, such as the west coast of continents, are among the most biologically productive areas in the ocean. Fisheries are often concentrated there because the food web is fueled by this nutrient injection. The west coast of South America is widely recognized to be the most productive parts of the ocean in terms of fisheries, and it's for this reason. Upwelling is not a separate phenomenon from surface currents. It is a direct mechanical consequence of wind-driven transport in a rotating system. And notice, tides do not create upwelling on this scale. Waves do not create upwelling on this scale. This is uniquely a wind and rotation process. Upwelling occurs when surface water diverges, when it spreads apart and leaves a gap that must be filled from below. But the opposite situation also occurs. Let's now imagine a scenario where Ekman transport causes surface water to move toward a region rather than away from it. This can happen in the open ocean between wind belts. For example, consider the region between the trade winds and the westerlies in the northern hemisphere. Trade winds blow from the northeast toward the southwest. Westerlies blow from the southwest toward the northeast. But because of the Coriolis deflection, the net Ekman transport under these wind systems can cause surface waters to move toward the center of the basin. When water converges at that surface, it accumulates. It cannot continue piling up indefinitely. The ocean surface can only rise so much before gravity acts to restore equilibrium. So instead of continuing upward, the water is actually forced downward. This process is called downwelling. Downwelling is the downward movement of surface water into deeper layers in response to surface convergence. Now let's connect this to biology and chemistry again. Surface water is generally warmer and lower in nutrients compared to deep water. When downwelling occurs, nutrient-poor water is pushed downward and nutrient-rich water remains isolated below. As a result, downwelling regions tend to have lower primary productivity compared to upwelling regions. Downwelling also plays an important role in transporting oxygen-rich surface water into deeper layers, influencing deep ocean chemistry and biology. Understanding convergence and downwellings helps you see that surface currents are not just horizontal features, they can actually drive vertical exchange as well. Now let's take a broader view of currents by looking at patterns across entire ocean basins. Global wind patterns are not random. Trade winds blow toward the equator. Westerlies blow toward higher latitudes. Hopefully you remember these predictable wind bands are a function of the uneven heating of Earth's surface. And that, of course, is due to Earth's curvature. And hopefully you remember these are the persistent and continuous winds that give the force that creates the surface currents. When trade winds push surface water westward in the tropics, and westerlies push surface water eastward at mid-latitudes, water begins to move in large arcs across ocean basins. But Coriolis, of course, deflects the path of these wind-driven currents. And then we have the issue of continents getting in the way. Water cannot flow through land. When currents encounter continental boundaries, they are redirected up the coastline. A good example is the Gulf Stream current labeled on the left diagram. It is located in the western North Atlantic along the east coast of the United States. Notice how the north equatorial surface current is pushing west toward North America, and then we see the Gulf Stream divert the water north. Currents approaching continents will always turn to move parallel to the continent. Because of Coriolis deflection that we just talked about, and continental boundaries that restrict flow within an ocean basin, these currents organize into large rotating system called gyres. There are 5 major subtropical gyres in the world ocean. In the northern hemisphere, they rotate clockwise. In the southern hemisphere, counterclockwise. Pause the video here and see if you can locate the 5 gyres on the left illustration. Can you name the 4 primary currents that make up the gyre in the northern Atlantic Ocean? If you email me the names of those 4 currents before our class period on this lecture, I will give you 2 extra credit points on your first exam. Before moving on, let's make sure we understand how everything is connecting. Wind initiates motion. Coriolis bends it. Ekman transport modifies direction of the water. Convergence and divergence creates vertical motion, and continents redirect flow. The result of these connected processes is large-scale circulation pattern that creates 5 gyres on the planet. I need to add one additional bit of complexity to our gyre system. It turns out that gyres are not symmetrical patterns of circulation. In every gyre, the current on the western side of the ocean is narrow, deep, and fast. On the western side, the current is broad, shallow, and slow. This phenomenon is called western intensification. Do you want to take a guess as to why this occurs? This asymmetry arises from the interaction between Earth's rotation and basin scale circulation. So yes, you may have guessed. Once again, it comes back to the Coriolis effect and one of the earlier characteristics we mentioned about it. The Coriolis effect gets stronger with latitude. So the deflection gets stronger as you move away from the equator. As the surface current moving along the equator approaches the continent and pushes water away from the continent, the Coriolis effect increases, and that compresses the flow of water into a more narrow and faster moving stream. The illustration on the left shows you the narrower Gulf Stream traveling north along the east coast of the United States versus the broader and slower moving Canary Current that flows along the western coast of Europe and Africa. Now we move from mechanics to consequences. Surface currents are not just moving water, they are redistributing heat on a planetary scale. The equator receives more solar radiation than the poles. If there were no redistribution of heat, equatorial regions would become much hotter and polar regions would be much colder. The atmosphere moves heat poleward, but the ocean plays an equally important role. Warm surface water in the tropics is transported toward higher latitudes by western boundary currents, like the Gulf Stream, which we just talked about, or even the Kuroshio current in the western Pacific. As this warm water moves poleward, it releases heat to the atmosphere. That heat release influences regional climate. So, for example, Western Europe experiences milder winters than regions at similar latitudes in eastern Canada. One contributing factor is that the northward transport of warm water by the Gulf Stream and its extension. When warm surface water transfers heat to the atmosphere, it modifies atmospheric pressure patterns, storm tracks, and evaporation rates. In turn, atmospheric circulation influences wind patterns, which feed back into the surface currents. So the relationship is a two-way system. Surface currents are shaped by winds, but they also influence the atmosphere. This feedback loop is part of Earth's climate system. So with this slide, you should understand that surface currents are a climate regulating mechanism, not just a physical oceanographic curiosity. Surface currents are the connective tissue of the upper ocean. They transport heat, which influences climate. They transport salt, which affects density and deeper circulation, which we'll talk about next lecture. They transport nutrients, which influence productivity. They transport dissolved gases involving or including oxygen and carbon dioxide. They transport floating debris and pollutants, concentrating them in some regions. One visible example of surface current convergence is the accumulation of floating plastics in subtropical gyres, often referred to as garbage patches. These are not solid islands of trash, but regions where surface currents converge and floating material accumulates over time. The photo on the left shows a picture of the Great Garbage Patch of the Pacific Ocean, which is larger than the size of Texas. Biologically, surface currents connect distant ecosystems. Larvae released in one region may settle thousands of kilometers away. Species distributions are therefore shaped by these transport pathways. Surface currents also form the upper branch of global ocean circulation. Without understanding them, we cannot understand how the ocean distributes energy and materials around the planet. So next, we move below the surface. Surface currents are driven by wind and shaped by rotation, but deeper currents are driven by differences in density caused by temperature and salinity. The surface ocean is only half the story. To understand global circulation fully, we must combine wind-driven motion with density-driven motion. That is where we go next. We will learn about deep ocean currents in the next lecture.